Hey everyone, welcome back to another explainer. I am so incredibly excited to guide you through today's topic because we're looking at the absolute foundational blueprint of modern deep reinforcement learning. Imagine it's 2013. A group of researchers at DeepMind unleash a single algorithm that does something people genuinely thought was impossible. With zero human-engineered features, this agent just looks at raw, unstructured Atari pixels, literally just the raw pixels on a screen, and it learns to completely dominate classical agents. It was an absolutely massive breakthrough that basically kicked off the Deep RL era as we know it. And today, we're going to tear down that exact architecture, the Deep Q network, or DQN, to understand exactly how it ticks. Okay, let's dive right into this. Here's our roadmap. First up, the Atari breakthrough. Second, the deadly triad. Third, 3 engineering tricks. Fourth, upgrades and pitfalls. And finally, the Deep RL blueprint. Starting off with Section 1, the Atari breakthrough. To really appreciate DQN, we have to look back at the mammoth problem they were facing in the early 2010s. In 2013, Volodymyr Minhath and his team presented a paper at the NeurIPS workshop. They showed off a Q-learning network trained entirely on raw pixels that actually beat classic agents on 7 different Atari games. Then, just 2 years later, in 2015, they extended this to 49 games and published it in Nature. This was huge. It was the very first time a single architecture, using a single set of hyperparameters, solved dozens of control problems straight from the screen. That spark led to continuous innovation, like the 2017 Rainbow improvements, ultimately solidifying it as the foundational reference blueprint we're still studying today in 2026. 100,800. Now, why does that specific number strike fear into the hearts of classical RL researchers? Well, traditional tabular QLearn needs to store a separate value for every single possible state and action combination. But if you look at a single Atari frame, it's 210 by 160 pixels with 3 color channels. Do the math, and that equals 100,800 features per frame. Tabular RL completely falls apart at just a few thousand states, let alone the billions of combinations possible in an Atari game. The scale of the problem was just impossible. The fix, which seems obvious in hindsight, was to replace that massive table with a neural network. But getting that simple fix to actually work, that took decades. Which brings us to Section 2, the deadly triad. So why exactly did this take decades to solve? Because simply slapping a neural network onto Q-learning introduces a fatal flaw, known as the deadly triad. Basically, if you combine 3 specific elements, your AI doesn't just learn poorly, it actively diverges. It just blows up. Element 1 is function approximation. That's our neural network trying to generalize across that massive pixel space. Element 2 is bootstrapping, meaning the network updates its estimates based on its own other estimates rather than waiting for the final actual outcome. And element 3 is off-policy learning, where the agent learns about an optimal strategy while actually following a totally different, more exploratory strategy. You put those 3 together, and you guarantee absolute instability. This antagonism made convergence practically impossible for years. Moving right along to Section 3, 3 engineering tricks. The real magic of those early DeepMind papers wasn't that they invented brand new math out of thin air. It was that they used 3 incredibly clever engineering tricks that finally defeated the deadly triad. Trick 1, experience replay. Trick 2, the target network. And trick 3, reward clipping. Literally everything built since is stacked on this base. So let's break them down. First up, experience replay. Think about when you're playing a video game. Consecutive frames are almost identical, right? If you feed those nearly identical frames into a neural network, one right after the other, the network is just going to overfit to that specific moment and forget everything else. To fix this, we use a ring buffer that stores around 1 million past transitions. During training, we don't learn from the most recent frame. Instead, we sample a mini batch completely uniformly at random from that massive buffer. It's a brilliant move because it completely breaks the temporal correlation and decorrelates the gradient updates. Without it, the network just diverges. Second, we have the target network. And honestly, the best way to think about the problem this solves is a dog chasing its own tail. In traditional Q-learning, the objective equation uses the exact same network to estimate both your current state and your target future state. But since you update the network on every single step, your target is constantly moving. It's totally impossible to learn. The fix? We keep a second, identical network called the target network, and we keep its weights completely frozen. We use this frozen network to calculate our targets, and then, every 10,000 steps or so, we simply copy the current active weights over to it. This gives us a nice, stable regression target for thousands of steps at a time. And the third trick is reward clipping. In Atari, the scoring is all over the place. Some games give you 10 points for a good action, others might give you 1,000. If you process those raw numbers, the gradient magnitudes are going to wildly fluctuate, and that one high-scoring game will completely hijack the network's learning. By clamping all positive rewards to +1 and all negative rewards to -1, we normalize those gradient magnitudes. Now sure, this is technically wrong if the actual size of the reward truly matters for the strategy, but it's perfectly fine for Atari, where basically only the sign, was this good or bad, is what really matters.
All right, Section 4, Upgrades and Pitfalls. Let's see how this is actually built.
So now that we have the core architecture, let's look at how it practically comes together in code. Building a DQN fundamentally requires these 4 steps, and it doesn't matter if you're running a fast little toy grid world or scaling up to 200 million frames of Atari. Step 1, initialize your replay buffer so it can hold those past experiences. Step 2, build your queue network. For a toy game, just a tiny manual multi-layer perceptron is totally fine. Step 3, code the DQN update itself, making sure you backpropagate through your differentiable network while utilizing that frozen target network. And finally, step 4, be outer loop, where your agent actually acts in the environment, pushes those new transitions to the buffer, samples a random batch, and periodically syncs up that target network.
But listen, there is a major pitfall we absolutely have to address: overestimation. Because Q-learning takes the maximum of estimated future rewards, and those estimates naturally have some noise, the network is heavily biased to constantly overestimate how good a state actually is. To tackle this, in 2016, Houda von Husselt introduced the Double DQN upgrade. It is just so elegant. You simply use your online active network to select the best action, but you use your frozen target network to evaluate the value of that action. It's a super simple drop-in replacement in the code, it consistently performs better, and honestly, it should be used by default. This fix, along with other additive tricks like prioritized replay and dueling architectures, eventually combined to form the famous Rainbow DQN in 2017.
Finally, Section 5, the Deep RL Blueprint. Let's zoom out for a second and look at the landscape today, in 2026. Standard DQN is rarely the state-of-the-art method of choice anymore. For continuous control, like getting a robot to walk, we use SAC or TD3, mainly because DQN doesn't have an explicit policy network. For high-throughput tasks or training large language models, we use PPO because it scales a lot easier without needing a massive replay buffer. And for offline RL, we use conservative Q-learning to avoid those bootstrapping blowups. But look closely, the lessons absolutely still travel. The experience replay and target networks we just broke down, they appear in SAC, TD3, AlphaZero self-play, and almost every single offline RL method out there. DQN might not be the final answer anymore, but it is the undeniable foundation. To wrap things up, I want to leave you with a bit of a provocative thought, pulled straight from a hard exercise in the source material. If you go and build this, how does the bias of your Q network compare to the true optimal value after 1,000 episodes, with and without that double DQNA upgrade we talked about? Just think about how early exploration and maximization bias can literally warp an AI's perception of reality. It really challenges everything we assume about how machines learn to value their environment. I hope this explainer gave you a super concrete, structured understanding of the deep RL blueprint. Keep learning, keep building, and I will see you in the next explainer.